Hello, we're the Oshkosh Additive Manufacturing of the Knuckle. Uh, we're here to talk about what we have done over the whole year. Uh, a couple of our teammates are Connor and John and Logan, and we don't have Dante on there, but Dante is also on there. And I'm Keegan, and this is Connor. So we're gonna go over a little bit of the agenda. I'm gonna be talking about the project background, the knuckle design, and Connor will be talking about the manufacturing results and some of the conclusions that we came to. For the project overview, Oshkosh has tasked us with the required steps to basically manufacture a part using additive manufacturing. They give us this space claim, and they want us to use some software and then use some type of printer to get this part model into the real world. So like I said before, Oshkosh gave us a negative space claim. So this is just showing like very key parts of where the knuckle will be designed on. So we have the upper control arm, the lower control arm, the bearings, the brake caliper, and the axle, all prominent points of the knuckle. And so our last year's group decided to go with the powder bed fusion printer. They thought it was the best printer that the university has to offer. It's basically what it does is it uses a laser beam to basically fire the metal powder into a part, and it basically takes waste product, and you can also recycle it back into the printer. So there's little to no waste. But it's also very nice for additive manufacturing and part printing for 3D printing because there's a bunch of huge benefits, and I'll get into those very shortly. So for the material selection, we went with grade 5 titanium. Lightweight properties of the material fit the part the best. We had some issues with thinking about oxidization of the metal because we wanted to basically stress relieve it to have it not be as because we saw that printing the part would be it was hard for the material, and so to stress relieve that and make the part as durable as possible. So for stress and weight optimization, we used a super mesh, and we were given some load cases by Oshkosh to then test those load cases on this negative space claim. And you can see that circular area there is that's where the knuckle comes into, and the bottom is the lower control arm, it's the upper control arm, and then the other side too. And so our team designed this block as kind of like where the optimization will start and kind of where key interests of that optimization will be basically removed to give us a ergonomic and lightweighted product. So here's some of the load cases that Oshkosh has tested: acceleration, some lateral some vertical, some rebound, and some braking forces. And these are just basically standard forces that would be required for, the knuckle to not, to basically have that stress and not overlap that stress, so it would cause failing. And so these tests basically would show where material was not needed to further optimize that block model, make it more ergonomic, and not use as much material to basically make it more cost effective and beneficial to the knuckle design. So this is our first part design. You can see that we went with a curved, basically studs on the left-hand side. There's the upper control arm on the right. There's some radii, some nice angles, some studs, and then there's the lower control eye and fillets, kind of flush it out more. And this is what we got for our first optimization results and how we designed the part in some CAD software. So this is the second part model. Given feedback from Oshkosh, we then took that and ran with it and further optimized the part, getting little chamfers on the studs, getting more inclined on that angle brake calipers, more fillets, basically more ergonomic on the middle. And yeah, and that's what we did with the second generation of that part design. So this is the optimization, or this is the stress results for the second part model. We used hypermesh, and the finite element analysis results are as shown. Basically, this shows that under high amounts of stress, the part will not fail in this particular von Miss stresses, so 2D and 3D load stresses, and we have the max yield and the yield stress on the corner there. So showing that to Oshkosh, they saw there was a bunch of blue. That blue designated we could remove a bunch more material. So we took that design again and ran it through hypermesh through our optimization software and developed a more thorough optimization on the second time around. And here we can see that there can be even more material removed from the part model. And from that part design, we went with a third gen part design, we reduced the size of the fillets, removed unnecessary materials. You can see that the incline on that brake caliper is now, all that material inside is removed, and we've flushed it out. So now there's even less material now, which is fantastic. And this is the results of that third part design. And here we show that the load cases can also withstand the stress of that part. The part can withstand the stress. So we went to Oshkosh and they're like, well, even more material can be removed because all that blue is still material that can be removed. It's still things. We still had to keep the prominent areas when more material can be removed from that part design.
So what we did was we started to look at we wanted to optimize just the areas where the critical geometries connected to the main hub of the part. So with each of those blocks, we ran optimization again. As you can see, these are those results. And we were able to really remove a lot of material and out sections that were not necessary. So here's more of those results. Looking from the other direction, you can see there's a lot of material that could still be removed. So another thing we did, we looked at sections within the part to see where we could internally remove material in certain sections. So here's a few of those. And we used them to see where we could really optimize our geometry and put curves in and stuff like that to reduce as much weight as possible. So with all that work, we come up with this as our final part design. As you can see, compared to the first one, a lot of material has been removed and the part is lightweight, but yet can still withstand the load cases. And we decided from here, this is about as good as we were going to be able to get with getting near that yield stress requirement for the highest load cases with the maximum stress. So this is just a picture of what the hub looks like on the assembly. So with that, we started to do small scale prints in order to actually determine that we can actually make this part. So we started off with doing a 1/3 scale, and we ran into some issues with holes being out of round and also some surface defects, even though the surface defects were determined to be due to a machine failure. But our main issue we ran into were thermal stresses that had built up, causing holes to deform and become out of round. So the 1/3 scale, we decided to do a 60% scale print to determine if the thicker walls would, reduce some of that distortion. However, we still saw similar issues in some areas with the part deforming. So then we decided to do it in plastic, a 1/3 scale as well. And this is where we really were able to determine that thermal stresses were to the same, because we saw, again, the same distortions in the same locations. So we decided to actually incorporate thicker supports into our part model before taking it to the program where a build structure and build plan gets generated. And with this, we saw excellent results with another 1/3 scale plastic print with the new supports. And you can see the areas that were deformed before printing, we did not see that with this. So then we did a 50% scale metal print, and we were able to successfully produce a small scale version of the part. As you can see, we didn't have any lifting in those areas where the caliper mounts on or distortion of the holes. So from here on out, we're ready to print a full-size part, and we know that we can now effectively manufacture one using selective laser sintering. And then we are also running material testing that way we can guarantee the strength of the endurance of the material against the published data. And then once all is said and done and the part has been machined, treated, the part will be put on the vehicle, and the testing will be able to prove that it can survive in service. So we'd like to thank our sponsor, Conor and Oshkosh, for allowing us to work on this project, Dave Labyak for advising our enterprise. And yeah, that's it. Thank you and have a good day.
Thank you.